Okay, so sorry about the crappy video last time, but I'm going to try to do this again. Okay, so Chapter 13, number 37. An object is fired vertically upward from the surface of the Earth, of radius re, with an initial speed vi, that is comparable but less than the escape speed v escape. Show that the object attains a maximum height h given by this equation. So, it wants me to solve for this equation. Basically, how you can do this is by using an energy equation, which would be 1/2, and since m is going to drop out, I'm just going to write it with m dropped out, minus g m e divided by re for gravitational force. This is kinetic energy, and then we have a final gravitational energy out here, and that is going to be divided by re plus its new altitude h. So once you do that, you can solve for re plus h. So I'm going to go ahead and write in that equation. This is done by multiplying re plus h out and then just subtracting the radius of the Earth from it. So you get negative g mass of the Earth divided by negative g me over re plus 1/2 vi squared. And then actually we have also negative re out here because it was re plus h. So now what you have to do is basically get it into the form of this, because this is the equation that they wanted us to derive. This is done by multiplying this by 2e, because we know that the escape velocity is actually the square root of 2gme re, and we need the escape squared, so we can just take the square root off of that and set it equal. And then re can be found by multiplying the common denominator, basically. Once you do that, actually everything drops out, but I'll go ahead and write it in real quick, where you have 2gme, because we multiplied in the negative 2, divided by 2gme over the radius of the Earth plus 1, or no, this is now going to be the velocity initial squared. So it actually fits in right nicely just right there. And then this, the re, is going to be multiplied by the bottom, so that's 2gme divided by re, and then re, well, that's actually plus, yeah, plus re vi squared. And these terms over the same denominator, these terms are going to drop out, so you add these two right here. So you're going to get re vi squared divided by the escape velocity plus vi, and that derives the equation. So basically that just shows that the height is equal to the equation they already gave us. After that, they just want you to plug in a couple of numbers. They say part B, a space vehicle is launched vertically upward from the Earth's surface with an initial speed of 8.76 km, which is less than the escape speed of 11.2. So basically this is really simple. You put in the radius of the Earth, which is some constant, and then the initial speed, which they said was 8.76 squared, divided by, the escape velocity, which they said was 11.2 squared minus 8.76 squared. And that gives you a value of, hold on, it's 10,036.85. So basically all you were doing was plugging in the numbers to get this value. Basically just using the equation to solve for a problem they wanted. Then you have part C. Now part C is actually done using the exact same energy equation, where you have mvi squared minus g me divided by re is equal to negative g me divided by re plus h. And here all you're doing is solving for vi, which I already have. So once you solve for vi, because technically, since it's a meteorite falling to the Earth, watch, let me read it. A meteorite falls to the Earth. It is essentially at rest with respect to the Earth when it is at a height of 2.51 times 10 to the 7th. So now that we have a height, we can just solve for vi. Oops. The equation for that, actually, once you solve for it, it's just some simple algebra. You get 2gme divided by the radius of the Earth, and that is subtracted by gme divided by re plus h. So you plug in all the values for that, because, I mean, most of these are constant anyway. The only one they give you, which is now a constant, is h. So all these numbers work out, and you get some value 9,994.18, and that is in meters per second, even though they give kilometers. Basically, I just worked out the conversion. So since this is actually viewed as a 2D projectile in a way, you can set the vi equal to what is going to be the v final when it hits the ground. So yeah, that pretty much sets that up. And then there's one last problem to the question, and that last problem is it's a what if scenario. Basically, assume that a baseball is tossed up at an initial speed, where the mass is really much smaller than that of the mass of the Earth. Basically, it wants you, and also it gives you another equation, which is an old kinematics equation. It wants you to compare this one to this one and see that they're basically the same. So yeah, and then that's divided by 2g. Now basically what I did for this, since, I mean, you're not really given a value for an initial velocity, but you could sort of make one up. I mean, say if you threw the baseball at an initial speed at about 5, all of these other ones are actually going to be, I mean, they're all going to be constants. You've got g, and then this has the g and the radius of the Earth in it. So basically, you plug in 5 for each of these vi's, and that should verify, I mean, assuming that we just give it that value, that'll verify that these equations are the same. And once you do that, you end up with a value of 1.27, I think, meters per second. Or no, that's just meters. You get 1.27 meters if you just use those values, and that's really the easiest way I could find to do that. So yeah, that wraps up the end of the question. Hope this one turned out better for you, Rob. Sorry.